Welcome back to Operational Research video series. In this video lecture on transportation problem, we present northwest corner method, one of the simplest and probably the oldest among all methods for determining initial basic feasible solution to a given transportation problem. Now, moving towards the solution of a transportation problem that has two parts. First, we determine IBFS, that is initial basic feasible solution by any of these methods, and then we improve on that solution and thereby determine the optimal solution by either stepping stone algorithm or UV method or MODI. In this video lecture, the task is to determine the initial basic feasible solution to this transportation table by northwest corner method. Before moving deep into the method, we have to check whether the necessary and sufficient condition for the existence of a feasible solution is satisfied or not. We know that the necessary and sufficient condition for the existence of a feasible solution to this given TP is that the transportation problem should be a balanced transportation problem. That is, the total supply should be exactly equal to the total demand in this given transportation table. We call it also rim requirement. So what is the total supply in this transportation table? Here we have three origins O1, O2 and O3 with supplies 60, 40 and 35. Therefore, sum of these supplies is equal to 135. Next, we also observe that there are four destinations with demands 30, 50, 40 and 15 respectively. The sum of them, that is the total demand, is also 135. Therefore, the total supply is equal to the total demand. That means the rim requirement is met. So, the given transportation table has feasible solution. Next, moving towards the first step.
We first move to the northwest cornered cell, that is left top cell of the matrix or transportation table. In this problem, the cell in the northwest position is this cell. At this cell, we have supply of 60 units and demand of 30 units. Therefore, only 30 units of demand can be met from the supply of 60 units. How? The minimum of 60 and 30 is 30. Therefore, we allocate 30 to this cell. Since we have fulfilled the demand of the first column, as 30 has already been allocated in that column to some cell or to some origin, therefore we discard the other elements of that column. We can also put a cross mark here. As 30 units of demand have been met from 60 units of supply, so the remaining supply is 30 units only. We consider the rest of the table that comprises of second column, third column, fourth column of the original transportation table. In the rest of the matrix, the northwest cornered cell is this cell. At this cell, we have supply of 30 units and demand of 50 units. Hence, within the demand of 50 units, only 30 units can be met as the supply is 30. In other words, the minimum of 30 and 50 is 30 and therefore we allocate 30 unit again to this cell. Clearly, the supply of source 1 or origin 1 has already been exhausted and we remove rest of the cells from the transportation table. As before, we put a cross mark on the right side. Also, since 30 units of demand has been met from 50 units of total demand, we have 20 units of demand left. Next, we consider the rest of the table and its northwest corner cell is this cell at 2, 2 position. At this cell, we find a demand of 20 units and supply of 40 units. Therefore, only 20 units of demand can be met from the supply of 40 units. So, another 20 units remain as it is from the supply, whereas the demand has been completely met. Therefore, we can put a cross mark as before. So, we also delete the rest of the elements along the second column. The matrix that we are left with is 5, 8, 6, 4 only. In this matrix, the northwest corner cell is this cell. At this cell, we can allocate the minimum of 40 and 20 as before. Therefore, we allocate 20 units here among the in between the supply of 20 units and demand of 40 units. So the supply has already been exhausted and you discard the rest of the elements along that supply or along the second row. And from 40 units of demand, we have met 20 units of demand. So another 20 is left with us. We are left with this matrix of sides 1 row and 2 columns, 6, 4 only. In that matrix, we can find the northwest corner at this position, at this cell. In that cell, we shall allocate as before the minimum of 20 and 35, which is 20, so as to exhaust all the demands of destination 3, and we are with another 15 units of supply from third origin or third source. You can observe that since the transportation problem is a balanced transportation problem, that is the total supply equal to 135 unit is equal to total demand. Therefore, at the last, we are left with same demand and same supply that we have to allocate at the remaining cell only. You can remember that in case of a tie, you can discard both the row and both the row and the columns and move diagonally. So the next task is to determine the total cost in initial basic feasible solution to this given transportation problem. You may note that the origin 1 to destination 1, you have to transport 30 units. Per unit cost is 4 units. So the total cost is 4 into 30, that is 120. Similarly, from origin 1 to destination 2, you are transporting 30 units. Per unit cost 7. So total cost is 210 units. If you find out the sum, of all this cost, you can find that the total cost will be 750 units only. One can note that the cells at which you have these non-zero values at the northwest corner, you call them allocated or occupied cells. The rest cells like these and these are unoccupied cells.